All right, we're going to take a look at the mean value theorem. This is the third of our theorems in this little theorem series. And if you're in my class, we're going to start with a warm-up to review the other two theorems that we've looked at. And if you're not in my class, you may want to advance the video a little bit and just get right into the mean value theorem. In this warm-up, you've been given a function, a cubic function, and you have been given an interval on which to work. And your job is to decide whether the following theorems apply. If no, tell which condition is not met. If you're in my class, I would suggest that you stop the video, do the problem, and then turn the video back on to check to see if you did the problem correctly so that you know what you're doing. So the extreme value theorem, remember, has two conditions. You have to have, number one, a closed interval. So the first question is, do we have a closed interval? That's yes. And this is in common with Rolle's theorem. You also have to have a closed interval. So check, check. You also have to have a function that's continuous on the open interval. And this is a power function, so it is continuous on the interval, and the same thing is true for Rolle's theorem. It's continuous on the interval. Now for the extreme value theorem, we can stop because there are only two conditions, so the criteria is met. So now we can determine the guarantee, what's promised by this theorem. Well, recall that if you meet the conditions for the extreme value theorem, the promise or the guarantee is that there will be an absolute max and an absolute minimum on the closed interval. So I'm going ahead with number two. If the conditions are met, apply the theorem. I'm not going to completely do the problem. I'll just kind of walk you through it. Remember, for the extreme value theorem, the candidates for being the place where the absolute max or min occurs are the endpoints and the critical numbers. The endpoints are given, so we would make a table, and we would have x, f of x. We have negative 2 and 3 as our two endpoints, so we have negative 2 and 3. Then the next thing we need to figure out are the critical numbers. Remember, we need to figure out where the derivative is equal to 0 or undefined. So we would find the derivative of this function, set it equal to 0, and find our any critical numbers. It looks like we might have 2, so let's just say we get x equal to a and x equal to b, and then those numbers go in the table, and then you plug those into the original function to compare the y values, because you're looking for the largest value of y and the smallest value of y. And you can confirm that by graphing it on your calculator to see. All right, let's go back and see if Rolle's theorem is going to apply. So the next thing we have to have, the function has to be differentiable on the open interval. That means on the inside of the interval, the function has a derivative. Well, this is a cubic function, so we know that that cubic function is going to be differentiable everywhere, so we're okay on that. And then the final question is f of negative 2 equal to f of 3. In other words, do they have the same y value at the endpoints? So if I substitute negative 2 in place of x, I will end up with negative 8. Substituting negative 2, negative 2 squared is 4, so minus 4, and negative 2 times negative 8 is positive 16. Hoping I did my arithmetic correct there. So negative 8, negative 4 is negative 12, plus 16 is 4. So that's going to be f of negative 2. Okay, and then substituting 3 cubed is 27, minus 3 squared is 9, minus 3 times 8 is 24. 27 minus 24 is 3. 3 minus 9 is negative 6. So f of 3 is negative 6, and f of negative 2 is not equal to f of 3. Therefore, Rolle's theorem does not apply. But remember, the promise of Rolle's theorem is, if it does apply, is that somewhere inside of that interval the derivative is 0. So if the Rolle's theorem did apply, we would set the function equal to 0 I'm sorry, take the derivative of the function and set it equal to 0 to determine in that interval where the derivative is 0. Okay, moving on to the mean value theorem. We're going to jump over these homework problems. I'll do those in class or on another video. Mean value theorem. Well, first of all, in math, the word mean should connotate an average. When you're told to find the mean of a set of numbers, you're really finding the average of a set of numbers. And in calculus, when we start talking about average, we start thinking about the average rate of change. All right, so that's going to come into play here. So suppose you drive a car 2 hours and you travel exactly 80 miles. What is the average velocity for the trip? Well, we know that distance is equal to rate times time, basic middle school formula. We know that we have traveled 80 miles and we have traveled in 2 hours. I'm sorry, I substituted into the wrong thing. We've traveled for 2 hours, so 2 in place of t. So I get 2r. So my average velocity is 40 miles per hour. Now, obviously, I did not travel 40 miles per hour every minute, every instant, every second of the trip because, well, I had to start the car. I had to travel from 0. I had to stop at certain points along the trip. So at some point during the trip, does the speed of the car, the speed, have to equal to the average velocity for the trip? So in other words, and instead of speed, I really would like to say the velocity. In other words, is the instant velocity at some time, does it have to equal to the average velocity? Well, think about the nature of an average. An average is not going to be a value that's greater than all the numbers in your list. So if I had 1, 2, 3, 7, 12, and I find the average of those 3 numbers by adding them and dividing by 5, the average is not going to be greater than 12, and it's not going to be less than 1. It's going to be some number between 1 and 12. So let's think about that. If the average velocity of my trip is 40 miles per hour, then that seems to indicate, since I couldn't travel 40 miles per hour the entire trip, every second of the trip, that seems to indicate that our speed or our velocity at some point had to be greater than 40 miles per hour. And obviously, when we start the car and we start at 0 miles per hour and we're getting up to our traveling speed, then we were traveling less than 40 miles per hour. So if we traveled less than 40 miles per hour, here's the speedometer, 10, 20, 30, 40, we'll put a star right there, 50, 60, 70, 80, blah, blah, blah. We said we had to travel greater than 40 miles per hour, so the speedometer had to go higher than 40, and obviously when we stopped we had to go less than 40. So at some point during the trip, the car actually had to travel at an instant 40 miles per hour. So does the car at some point does the instant rate of change have to equal the average rate of change? Yeah, kind of common sense there. So if we extend that into a problem, you're traveling along an interstate and you have to stop at a toll booth. So here you are at toll booth number 1. It's Thanksgiving, you're going to Grandma's house, and you hit the toll booth on the turnpike, and then you get your ticket from the ticket taker, ticket giver outer, whatever you want to call it, and then you go to toll booth number 2. When you arrive at the next toll booth, which is right here, here's your friendly little toll booth taker. Thank you for giving us money. When you give the money to the toll person, the person in the toll booth returns your toll ticket as well as a speeding ticket. How can the principle in the first example be used by the toll clerk to determine that you were speeding? Well, they can easily determine, they know the distance between the two toll booths. All right, so they know the distance, and they can look at the time on your little ticket that they gave you, time. And if they know your time, they can figure out your average velocity by dividing distance by time. So let's say that the speed limit is 55 miles per hour. Well, if your average speed or average velocity is 55 miles per hour, then you had to be speeding because you had to go higher or greater than 55 miles per hour. So yes, it technically is possible that they could use this principle to determine whether or not you should get a speeding ticket, because remember, the big idea here is that your average rate of change, that's how fast you averaged on your trip, at some point has to equal to your instant rate of change. And that's kind of the principle, it's not kind of, it's the principle behind the mean value theorem. So the two examples above or on the other page illustrate the mean value theorem, which says the average rate of change, the ARC, on an interval of a function, and notice that the interval is a closed interval. I have the conditions written below because remember with our theorems the conditions are important. I have a closed interval. The average rate of change on an interval of a function is equal to the instant rate of change at some point on the open interval. So here we have closed, and this says somewhere on the inside of the interval there is a time at which your instant rate was equal to your average rate. All right, let's go ahead and jump to the conditions before I debrief that even further. The two conditions that must be met before the mean value theorem can be applied: number one, the function must be continuous on a closed interval. So technically you could break that into two conditions if you want to. Just like the extreme value theorem and Rolle's theorem, you have to have a closed interval. And just like the extreme value theorem and Rolle's theorem, the function has to be continuous on that closed interval. So you can think of it as one condition, or you can think of it as two different ones. Secondly, like Rolle's theorem, the function must be differentiable on the inside of the interval. In other words, it doesn't matter whether or not the function is differentiable at each endpoint. The function has to be differentiable on the inside of the interval. So keep in mind, you want to look at these theorems and remember the similarities and the differences between the conditions of the extreme value theorem, Rolle's theorem, and the mean value theorem. All right, so let's get back to the mean value theorem. So we have our conditions that must be met, and if those conditions are met, then the promise is what we see up here. At some point, the instant rate of change, that's what I have right here, the instant rate of change. Now we know in calculus the instant rate of change is derivative. So the derivative at a particular value, in this case I'm calling it c, is equal to the average rate of change, which is just good old-fashioned Algebra 1 slope, change in y over change in x. Another way of stating this is, so notice I'm giving this to you in words, I'm giving it to you in symbols, I'm giving it to you in abbreviations. Another way of stating this is, on a given interval, there must be, again, assuming that the interval meets the conditions, there must be at least one point c, or this is really one value, c, between a and b, where the slope of the function at c matches the slope of the secant line connecting a and b. You may be going, whoa, where's that all coming from? Well, remember, derivative is slope of the tangent line. So slope of the function, that would be slope of tangent, which is your instant rate of change, your derivative, matches the slope of the secant line. And remember, slope of the secant line is the average rate of change. Secant line connects to the two endpoints. If you don't remember what a secant line is, it connects the two endpoints. So on the graph that you see here, I have a closed and continuous interval. It's starting at A and it's stopping at B. So that's my closed interval, and you can see by looking at the graph that the function is continuous. So the first thing I do is I look at the secant line, which I'm going to dot or trace over in blue. The slope of the blue line, which is the secant line, is the average rate of change. So by visual inspection, I'm wondering, well, are there any times, if you want to think of it as times, that's an easy way to think about it. Are there any times on this graph at which the instant rate of change is equal to the average rate of change? In other words, I'm looking for parallel lines because parallel lines have the same, the same slope. So you can see, and I'm going to highlight those in red, that at this value, approximately, this is an approximation, I'm kind of eyeballing it, at these values, the instant rate of change, there were 3 times at which my instant rate of change was equal to my average rate of change. So that would be like you're traveling on a trip to Grandma's house at Thanksgiving, and on that trip there were 3 times at which, if your average rate of change was 50 miles per hour, there were 3 times at which your speedometer actually hit 50 miles per hour. All right, let's apply that mathematically or algebraically. Now, if you're in my class, this is not in your packet. You're going to do this on a sheet of notebook paper. So number 1, decide if the mean value theorem applies, and if so, find any values of C. In other words, any times at which the instance equal to the average. So the first thing I have to consider is, do I have a closed interval? That would be yes, from 1 to 4. Is the function continuous on that closed interval? Now notice, in this function I have f of x. If I get a common denominator, I would have 5x minus 4 over x. And notice I have something very dangerous here. I have an x in the denominator. So this function is not continuous at x equal to 0. There's a discontinuity at x equal to 0. And we said that the function has to be continuous on the closed interval. So the next thing we look at is 0 on the interval? No. 0 is outside the interval because the function that we're thinking about, or the closed interval we're looking at, is from 1 to 4. So even though there's a discontinuity, the function's continuous on the closed interval, so that's a check. All right, so be careful with that. Then the next thing we have to decide is whether or not the function is differentiable on the inside of the interval. Well, again, the only place that we'd have to worry about the function not being differentiable is at x equal to 0, and that's not inside the interval, so we're good to go. Now, applying the theorem, remember, this is what you want to keep in mind. We're trying to figure out when is the average rate of change equal to the instant rate of change. The average rate of change is good old-fashioned Algebra 1 slope, and instant rate of change is the derivative of the function. So the average rate of change would be f of 4 minus f of 1 over 4 minus 1. And the instant rate of change is the derivative of the function. So this is 5 minus 4x to the negative 1. The derivative of 5 is 0, and the derivative of negative 4x to the negative 1 is 4x to the negative 2. F of 4, by substituting into here, that would be 5 minus 1 is 4. F of 1, substituting 1 in here, 5 minus, what am I dividing by here? Sorry, I substituted 4 divided by 4 is 1. 5 minus 1 is 4. Substituting 1, I get 5 minus 4, which is 1 over 4 minus 1, which is going to be 1. Now look what I'm doing. I'm moving the x to the negative 2, moving that down to the denominator. Cross multiply, I get x squared is equal to 4, so x is equal to plus or minus 2. Now one might think that there were 2 times that the instant rate was equal to the average rate, but look back at the interval. Negative 2 is not in that interval, so I would say instant rate of change is equal to the average rate of change at x equal to 2. So there was a promise that at least once, it can happen more than once, but the promise is that it will happen at least once. All right, let's take a look at the second example. Okay, we're going to go, we have y equal to sine of x. We have a closed interval. We know that sine x, if you think about the graph, is continuous everywhere. We know that sine of x is differentiable everywhere. So all of the criteria are met. So there is a promise that at some point, at least one point, the instant is equal to the average. So start with your guiding. Average rate of change is equal to instant rate of change. That means slope and derivative. So I have sine of pi minus sine of 0, there's my change in y, over change in x, pi minus 0, is equal to the derivative. The derivative of sine is cosine of x. Alright, simplifying that, the sine of pi, the y value, remember sine is the y value, so that's going to be 0 minus 0 over pi. And that's going to be 0 equal to cosine of x. And on this interval, the cosine, the x value is 0 at pi over 2. It's also at 3 pi over 2, but look at your interval. This is only going from 0 to pi. So we would say the instant rate of change is equal to the average rate of change at x equal to pi over 2 by the mean value theorem. All right, let's take a look at a couple more things in your packet. On page 7 in your packet, we have a series of functions here, and we want to, if the conditions apply, we want to actually show where, by drawing lines, and you may want to use straight edges for this to help you. We want to see where the instant rate of change would equal to the average rate of change. So I'll do like 1 or 2 of these, and then you can handle the rest. In problem number 1, you can see that we have a closed interval starting at 3 and stopping at 7. The function's continuous and the function's differentiable. So now I don't have a straight edge here, so I'm going to do the best I can. There's my secant line as the blue line. It's a little bit off, but you get the idea. Now what I'm trying to figure out, and again I would use a straight edge if I were doing this on paper, is there a, well, we know for sure there is going to be, by the mean value theorem, there's at least one time at which the instant is equal to the average. So I'm trying to draw a tangent line that's parallel to the given line, and it looks to me to be, if I just eyeball this, that's not going to do it, maybe about there. So at that value, it's an approximate value, it looks like it's about, at least I'm estimating it to be 5. Okay, your graph, your sketch may be a little better than mine. And I don't see any other times where the tangent line would be parallel to the secant line. In this graph, well, I guess if we go down, number 2, same thing. We have a closed continuous differentiable interval. There's my secant line. And in this case, it looks like there's at least twice, probably about here and about here, at which, so there are 2 values, and I'm saying about here and about here, that the slope of the tangent line is equal to the slope of the secant line. And then the other 2 functions, the mean value theorem doesn't apply because the function is not differentiable in the next one at 4, and not continuous at 5. Oh, actually, they tell us to start from 5 to 8, so that one would work. So this is the mean value theorem. Hope that helps you out. Watch as needed.